So the goal in experiment 8 is to conduct some aldol condensations. For the purpose of the lab handout, I just ask you to tell me what the products would be for a couple of condensation reactions and to draw the mechanism under acidic and basic conditions. So we'll go over all of that stuff. So the simplest example for an aldol condensation would be the self-condensation of a 2-carbon aldehyde, ethanal, or the common name would be acetaldehyde. Generally speaking, we use a base like sodium hydroxide to deprotonate in order to form the enolate. Our intermediate that we expect to form looks like this, and we call this the aldol because it's part aldehyde and part alcohol. If we want to number our carbons in the product, we see that there are 4 carbons, and that makes reasonable sense because each of my aldehyde fragments is 2 carbons. If I'm combining 2 of them together, then my new product should be a 4-carbon product. Our understanding in general is that the aldol product isn't particularly stable, and it undergoes an elimination reaction where we lose the OH group, and that leads us to a different type of product. This is our alpha-beta unsaturated, in this case, aldehyde. So it's most common to see this reaction take place for basic conditions, but we can also see it under acidic conditions. So now I'll draw the mechanism for the reaction under both acidic and basic conditions. So just to visualize, I'm going to draw the 2 aldehydes in different colors so we can at least see in the product how things are taking place. I'll draw the bond between them in blue. And initially, oops, let me start that again. I'll make the molecule red, the bond in blue. So then initially we form that aldol, and the bond that we newly formed is the one right there. And then ultimately after elimination, we'll get the alpha-beta unsaturated product. Like that. So if I'm numbering carbons, 1, 2, 3, 4, and here in our intermediate, 1, 2, 3, 4, and then in the product, 1, 2, 3, 4. All right, so then let me draw the mechanism for this reaction. I'm not going to use different colors for the 2 now. I think it'll just make it more confusing, but hopefully you can see from the product formation what's going on. So this is our proposal. 2 identical aldehydes react together under basic conditions in order to form the alpha-beta unsaturated aldehyde. So we'll start with enolate formation. So remember, I'm not deprotonating the aldehyde hydrogen. That one's not terribly acidic. I'm deprotonating adjacent to the carbonyl carbon with 3 arrows. 1, 2, 3. And that's how I get the enolate to form. And at that point, the enolate form will be able to attack the other aldehyde molecule. And then you'll see this 3-arrow pattern again here, 1, 2, 3. And that'll get us on our way towards the aldol. I regenerate the CO pi bond in the attacking group. And then the one that got attacked is temporarily an O minus. Under basic conditions, you really want to make sure you're tracking whether you have OH minus at that moment in the reaction or H2O. In our first step, OH minus received a hydrogen, so right now it's back to being water, so that's our reasonable proton source. So we can protonate our O minus with that, and then that'll give us the aldol. We're basically doing an elimination reaction in the next step. So again, keeping track of whether you have OH minus or water, we're back to having OH minus. And then again, a 3-arrow mechanism. That looks an awful lot like E2 that we're doing, and that will lead us back to our product finally. So notice 3 of the 4 steps are these triple arrow steps, and that's a really important thing to focus on when you're thinking about the mechanism. So all of that was what happens under basic conditions, which is the most common version of this reaction. But we can also have aldol condensation under acidic conditions. So in general, when we're talking about ketones or aldehydes, we say that they can exist in 2 forms, the keto form, which has a double bond O, and then the generally less stable enol form. And enol is coming from alkene plus alcohol. So under acidic conditions, I can't kick anything out easily. I certainly can't kick off OH minus like I did under basic conditions, and I can't really show any negative charges at all. So we're going to see that enol becomes involved in this process a bit more. So let's say that our plan is still the same. We're going to react 2 identical aldehydes together. But this time I'll say that the reagent is H3O+. Ultimately, we're going to get to the same product, but it'll be a little bit different. And typically, I think I've said this a few times before, typically the acidic condition version of the mechanism involves substantially more steps. Okay, so what's going to happen here in this reaction? Well, this will look more like some stuff we've seen in earlier sections. I need to activate the carbonyl so that it's susceptible to attack by a weak nucleophile. So we'll start by protonating the carbonyl, and this will be the aldehyde that's going to behave as the electrophile. So now it's double bond O, H plus, and then we're going to use the enol form of the other aldehyde in order to attack. So now I'll push in the lone pair from the oxygen and use that to push the pi bond outward in order to conduct a nucleophilic attack. Oops. From there, I'm going to flip things around so the attacking piece is on the left-hand side. From there, what I should have is OH plus on the attacking group, and then OH on the adjacent group. So now I want to get to the actual aldol. Remember, under basic conditions, I was saying you're trying to keep track of whether you have OH minus or H2O. Under acidic conditions, you're trying to keep track of whether you have H3O plus or H2O. So we gave up an H plus earlier in the mechanism, so we're back to being H2O here. And so now, after deprotonation, that'll give me my actual aldol product. Like that. So under basic conditions, we just deprotonated at this point, and we were able to kick off the OH group. Under acidic conditions, remember, I'm going to need to protonate the OH group in order to make it a good leaving group, so we're going to do that next. And same thing, keeping track of whether you have H2O or H3O plus is an important part here. So we know we want that OH to go, so we're going to give it a proton. And now we have the protonated form of the aldol, and then that sets us up for the water to leave, which gives me a carbocation. And at this point, the hydrogens next to the carbocation are made a bit more acidic. And then we can imagine this water molecule that we just kicked off will be able to act as a weak base to deprotonate in what more or less looks like an E1 reaction. That gives us our CC pi bond to create the alpha beta unsaturated, in this case again, aldehyde. So you can also use ketones as our source of enolate, and when we use ketones as our enolates, then the reaction becomes a Claisen-Schmidt reaction instead of an aldol condensation. Nothing really changes in terms of what takes place, but now we'll give it this different name. The most important thing about the ketone is it will not self-condense. Meaning I can't just react two acetone molecules together and expect them to react to form an aldol product. Just the bulk of having carbon chains on both sides is going to prevent that. So that actually makes ketones more desirable reactants because we can control exactly what's going to happen. So the best reactions that we can do that are more or less classified as aldol reactions are ones that are only going to produce one product. So if I use my ketone as the molecule I want to have turn into an enolate, and then I partner it with an electrophile that can't form an enolate, then that ends up being my ideal circumstances. So if you think about a reaction like this, the ketone can form an enolate at either of its alpha carbons, one away from the carbonyl, but the aldehyde alpha carbon can't be deprotonated, right? There's no hydrogen there to remove. So the result is I can't make an enolate out of an aldehyde. So this is kind of an ideal version of the aldol condensation because the ketone won't self-condense, and the aldehyde can't turn into an enolate. So this results in a situation where I actually can only end up with one possible product. And that's what's ideal when we're looking at this sort of reaction. So that's something that we're able to see take place in these reaction types. So that's a really convenient feature, and so generally you want to say if the enolate's a ketone, I won't self-condense, I'm only going to attack the electrophile, and if the enolate's coming from an aldehyde, I still need to expect some amount of self-condensation. So then really the last thing that we want to talk about here is what's called a crossed condensation, and so really here what we're describing is when we react two different aldehydes together. And this is a good way to think about what's really taking place in the aldol condensation, but also it's going to point out the non-ideal situation for an aldol where we get a complicated mixture of products. So let's say, for example, we want to see what happens when we react together the 2-carbon aldehyde, acetaldehyde or ethanal, with the 3-carbon aldehyde, propanal, and let's say that we're talking about it happening under basic conditions. So let's label our two reactants as A and B. And so in this case, with aldehydes, we expect self-condensation, so we should get a product resulting from A attacking A. We should also expect a product from A attacking B. Then we should expect a product B attacking A. And then lastly, we should expect a product B attacking B. So I'm going to go straight to the alpha-beta unsaturated products here. As you're getting used to this, you might feel like you're going to want to draw the aldol first just to kind of track what's going on, and that's totally okay. So something that I have in mind before I even start here is the carbon count for each of the products. And I can keep track of that because it's just going to be the sum of the total carbons that I'm working with. So A is a 2-carbon aldehyde, so the self-condensation product should have 4 carbons. So 1, 2, 3, 4. Alpha-beta unsaturated means that the pi bond is 1 away from the carbonyl. A attacks B should now have 5 carbons, so that's 1, 2. Then I'll draw the new bond in blue. And then B is 3 carbons, 3, 4, 5. All right, and then when B attacks A, 1, 2, and the third carbon I'm going to point down because that's not a carbon that's involved in the reaction, so I just get it out of the way. Again, we know it's alpha-beta unsaturated, and then 2 carbons. So we can see where the new CC pi bond formed and how many carbons are coming from each reactant. And then lastly, when B attacks B, same thing. I'll tuck that third carbon down knowing that it's not involved. We can show our, oh, it doesn't matter, I guess it's the same. 1, 2, 3, and then there's my CC pi bond. So as I'm thinking about what's happening, tracking the total number of carbons will be pretty helpful to make sense of what's going on. So that's really all that's going on with experiment 8. It's just asking you to practice drawing the mechanisms for aldol condensations or Claisen-Schmidt condensations, and then making sure you understand the process for drawing the products